Hi, we're Golf Ball Search and Rescue Gold Team.
We are responsible for designing a robot that can detect golf balls, navigate to them, and collect them.
My name is Kevin Springer. I'm a mechanical engineering student and I was responsible for modeling and analysis.
My name is Sean Gallagher. I'm also a mechanical engineering student responsible for the motor's power system and the collection mechanism.
I'm Alexa Keen. I'm a computer science student, and I was responsible for the navigation and path lighting.
My name is Andrew, and I am also a computer science major, and I'm responsible for image recognition of the golf balls and the boundaries.
My name is Jimmy Cabrera. I'm a mechanical engineering major and I was responsible for the fabrication and metalworking.
What separates this engineering project from what one might accomplish in their garage is detailed CAD modeling and stress analysis. Despite mostly working remote from one another, we were able to collaborate and form well-defined CAD models using SOLIDWORKS. Through this program, we were able to illustrate our ideas to one another and ensure there would not be any unforeseen interferences. We kept updated models throughout the project and shared them with each other in order to expound our ideas. Once we felt our CAD model was fully defined, stress analysis was done by creating simplified models and importing them into ANSYS. Unfortunately, our model was too complex for the student version, though this problem was overcome by creating simplified versions which were used just for stress analysis. Once the best trade-off was found through parametric analysis and mesh refinement, a worst-case stress scenario was examined by placing all of the weight on one side of the frame. Even under these conditions, our frame and fasteners passed the static structural test with a minimum factor of safety of 15. Another aspect of the project I worked closely on was terrain traversal and the associated steering. We settled on wheels for terrain traversal as they were cheap, readily available, and easy to work with. Casters were chosen for the driven wheels as the rotation of the robot by the drive wheels would cause stress on the driven wheels if they were unable to rotate on a vertical axis. Differential steering was chosen as this was the simplest form of steering available and the easiest to implement and integrate with the controls. Lastly, I worked closely on the cargo release system. The most effective method of release was settled on as dropping the basket containing the cargo, as this contains the least moving parts, as well as allows for easy operation by the user. Instead of collecting loose balls scattered on the floor, the user would just pick up the container off the ground. Our limitation in this respect was the release device available to us was flimsy and would be unable to support the weight of the cargo. We went through several iterations of design before settling on the device simply preventing the container from rolling off the front of the vehicle during normal operation, as this incurs the least possible stress on the release device.
The motors used are 12-volt DC brush motors with specs of 300 RPM and 233 ounce-inches of torque. This allowed a 20-pound vehicle to move at roughly 5 feet per second. The motors had an offset shaft that allowed for adjustable wheel height and also included Hall effect encoders. These motors were connected to a Cytron dual motor driver that used PWM input and MOSFET H bridges to control the speed and the direction. The motor driver had a max current limit of 10 amps for each channel. A 12-volt 3S LiPo battery powered the motor driver and the payload release mechanism. The release mechanism needed a DC to DC buck-down converter to regulate the voltage down to 7 volts. The Raspberry Pi was powered by a 5-volt power bank, and the Arduino Mega was powered by a 9-volt battery. A power switch and battery percentage indicator was added for better usability. The retrieval mechanism consisted of a laser-cut acrylic disc set that was spaced to capture the golf balls when it was rolled over. The spacer was 3D printed to ensure uniformity and allow for interlocking. The square profile of the disc axle ensured the entire mechanism would rotate as a unit. This square axle was a challenge to connect to the circular pillow block bearings. An adapter was 3D printed to resolve this. The disc diameter was designed to be larger than the wheel diameter, which caused the disc to always be in contact with the ground. This eliminated the need for an additional motor to spin the roller. Specially designed and 3D printed prongs were used to dislodge the collected balls into the container. If done again, the roll would be mounted on a suspension to allow balls in divots or ground depressions to be captured.
In this first image, you can see the final product that we took to the competition. I was manually tasked with the fabrication and the assembly of the frame of our vehicle. In the second image, you can see the initial design of the frame. Here it was assembled with T-slot and the initial caster mounts that we had. Here's another image of the caster mounted to the frame. One of the problems that we ran into, the motor mounts had a smaller hole diameter than the hardware that was provided with the T-slot. So I go ahead and drilled a 1/4-inch hole to the motor mount, which fit perfectly to allow our motor mounts to be mounted to the T-slot with the hardware that we had. In image 4, you can see the mounts for the bearings on the basket, which was our storage mechanism. These were mounted onto the basket. Now you can see the basket mounted onto the frame, and you can see how the casters are now on the side of the vehicle instead of parallel with the vehicle. This changed because once we installed the basket, we realized that we needed more room since the casters would swivel and it was hitting the basket. This was the final assembly for the frame. In image 7, you can see that I added some front guides. We needed about 2 inches on each side. After that, after adding the guides, we were getting a lot more balls, but we encountered a problem. Whenever the robot would approach a ball at an angle, the ball would slip right in between the caster and the pickup device, as you can see in this image. I added some side guides or walls to prevent that from happening. Instead, the balls would hit the guides and it would be directed to the pickup mechanism. One of the last things we did before the competition was doing wire management or cable management, and I did that together with Andrew, one of the CS students on the project. The last few things that we did on this was during the competition. The first problem we encountered, the rollers were too high and it wasn't rolling perfectly on the grass, so it was missing a few of the balls. So in the front casters, we raised the vehicle to put more pressure on the rollers, therefore the pickup mechanism could pick them up more efficiently. The last adjustment that we made during the competition, which was actually for our last run, we were struggling a little bit with traction. So I installed some screws in the wheels, which really helped, as you can see the grass stuck in the screws. This helped our vehicle gain more traction, and in the last run we were able to pick up about 25 balls in 8 minutes.
To begin, for the golf ball detection and vision portion of our project, I used the Google Cloud Vision API to create a custom-trained machine learning model to detect golf balls. With the Google Cloud Vision API, I was able to generate a TensorFlow Lite object detection model, which is highly effective for our Raspberry Pi as it requires lower computational power to detect golf balls in comparison to a regular TensorFlow model. Before training our TensorFlow Lite model, I also had to collect images and take pictures of golf balls in our competition field. In total, I was able to collect 609 images of golf balls that were on our competition field, as well as images taken from my home and from Google searches. Afterwards, I had to generate and label bounding boxes around the golf balls within my dataset. Google provided me with 20 compute hours, which allowed me to create a best trade-off model, as well as a model that sacrificed speed for accuracy, and vice versa. I was then able to quantize my TensorFlow Lite models, which is a process of reducing the memory requirements and computational cost of our neural network. This further allowed me to use the Google Coral USB Accelerator, which is a tensor processing unit specifically designed to outsource the computational power from our Raspberry Pi CPU to the accelerator. With these steps completed, I was able to run my object detection script in Python, and I was able to achieve approximately 18 frames per second with detecting golf balls on the quantized lower latency TensorFlow Lite model. As for boundary detection, our team decided that the color red would be our indicator for our robot to stop and reevaluate its surroundings so that it would not go out of bounds. With this task, I utilized Ho transformations, which is an algorithm designed to detect straight lines, as well as red detection on the HSV color space, which also creates a mask that will only highlight the color red. With these parts completed, I was able to provide our autonomous vehicle with the ability to find our golf balls and stay within the 75 feet by 75 feet boundary.
The original plan for navigation was to use a hybrid path plan that we developed to have our robot navigate in a square-shaped spiral for partial coverage of the field, and through the use of image detection, deviate off the path slightly to collect golf balls along the way, primarily using ROS2 software library. I used Gazebo to simulate the results of my logic and navigation. I started by using the motor encoder information to determine the robot's location, and created goals on the field using an XY coordinate system to create the square-shaped spiral path. I started with a full coverage path, which guaranteed complete ball collection, but also meant the robot would have to cover every square foot of the field. Due to the size and speed of the robot, this algorithm was very slow as a result. Once the vision aspect of our robot was developed and integrated in our simulation, I was able to remove some of the goals on the path plan to cover less of the field, and only navigate off the path if a golf ball was detected within range. This algorithm was much quicker but lessened the accuracy. At best, our robot would still miss at least 2 golf balls. This was mostly due to a blind spot in the robot's field of view when turning corners. Once we had the physical robot for integration, I ran into some other issues. The Raspberry Pi had trouble consistently receiving the motor encoder information from the Arduino Mega. Also, the kinematic formulas used to determine the robot's location had a larger than anticipated error due to slippage. This was increased even further due to our robot's traction issues. Also, our roller had trouble collecting balls in the field where the ground was not as flat, which was a problem since our path plan did not use any backtracking. This led to the decision to change our path plan to random search. This is where the robot would travel to golf balls as detected or travel straight. As a result, red line border detection was necessary to stop our robot from going out of bounds. In simulation, this change went smoothly, and our robot was able to quickly and efficiently collect all the golf balls on the field. This algorithm did, however, require manual navigation to the drop-off location. When testing on the physical robot, we had a couple more issues that arose. Our processing power on the Raspberry Pi caused our image detection to have a slight delay, and decrease in accuracy. Hindsight, the Jetson Nano might have been more compatible with ROS 2. Another issue with our image detection was impacted by the speed and bounce of our robot on the field. The faster our robot traveled increased the speed of which the image needed to be captured and processed to turn the robot for navigation. Even with these adversities, as a team, we decided to prioritize speed over accuracy and had great results. At peak during the competition, our robot was able to collect roughly 0.047 balls per second.